Finite state machines. A finite state machine is sometimes called a finite state automaton, or in plural, automata. And so you often hear or see the acronyms FSM and FSA for finite state machine, finite state automaton. What is a finite state machine? It's formally defined as a system containing a finite number of states, a transition function driven by input producing output. There are two types that are used in building electronic circuits. What are known as the Moore machine, which is an output that depends only on the present state of the machine, and the Mealy machine, which is output which depends not only on the present state but also the input. Automata have been built for a long time prior to the modern era of computers. Early automata were mechanical, and they were driven by some mechanism, driven by energy in the form of water, air, and steam. In the 20th century, they were driven by electricity, and that's what kinds of automaton in the form of machines that we're used to today. Consider the pneumatically or air-driven machines created by Hero of Alexandria. Hero created multiple designs of various forms of mechanical apparatus driven by forced air. Let's go ahead and take a look at one of them. This is a design for a machine entitled A Bird Made to Whistle by Flowing Water. Let's take a closer look at this mechanism. We have flowing water coming out of the head right here, and that provides the energy source. As the water descends down through a funnel into this closed box, it forces air up through this mechanism where you see the bird and the tree. And what this essentially does is it takes the air and forces it through a pipe that has a small hole in it, thus producing a bird sound. Charles Babbage in the 1830s created designs for two major kinds of computers: the difference in the analytical engine, with the mathematical and programming help of Ada Lovelace, who was Byron's daughter. We finally end up in our discussion with a modern computer in the formal definition of the finite state machine, along with some examples. The modern era of computation, with its theoretical underpinnings, began in the 1930s with mathematicians such as Turing, Church, and Post. The finite state machine can be seen as the first basic theoretical or virtual computer containing all the requisite elements. Many devices, as we'll find out, use finite state automata for their operation. All right, let's start our history out at the beginning with mechanical automata. We've already seen a simple automaton created by Hero of Alexandria. Other historical automata include clocks and a large number of mechanical devices using hand power or clocks for the driving force. Let's consider the following photographs. This photograph is from the Deutsche Museum of Technology and is of a mechanical trumpet player. It was designed and built by Frederick Kaufmann in 1810. According to documentation that you find on the museum website, The trumpet player puts the trumpet to his lips by moving his arm and then removes the instrument after playing. The device is driven by spring motion. There's a brass drum containing metal reeds. This drum rotates and then a sequence of musical notes is heard. Let's take a bit of a closer look at the automaton. The second figure shows the automaton with some parts removed, and you can definitely see a hand crank that's right here. This hand crank is what basically creates the energy in the form of spring motion. So this winds the spring. And then if we look at the back of the automaton, we can see the rotating drums and the pipes. Let's take a bit of a closer look at this right here. There's the head with the trumpet. You can see bellows. You can see the rotating drum. On the left, you can see the hand crank. Okay, it's noteworthy to view this kind of automaton like Pascal's and Leibniz's calculation machines, which were in the prior century, as the mechanical precursors of the modern-day computer and of its theoretical models, such as the finite state automaton, which is the subject of this lecture. The machine was able to take a driving input, in this case from the hand crank, store the future input in the form of spring energy, and then drive the trumpet player computer into a sequence of states. All right, let's proceed on to the analytic engine, created or designed by Charles Babbage, but not actually created until much later. Charles Babbage designed but never fully implemented and produced the analytic engine, which contains the basic elements that are found in today's computer. The engine contained all the basics. It contained input, output, mill, and store. The input, like the hand crank of the trumpeter, drove the machine forward. Also, the input contained the program that was to be executed. This program was stored on punch cards, which is a technology obtained through the Jacquard loom of the very late 18th century. The mill performed the functionality or the calculations of the program, and a very important aspect of this machine, unlike the trumpeter, is its ability to work between the store, which is a storage of variable values, and what we might call the memory today, which you might find on the computer disk that you have or the memory chips, and the mill. It is this ability to store values, inspect them at will or read them, and compute based on these values and along with the input, which create a full-fledged ability to perform computation. The output lies at the very end of this logical computing chain or pipeline, showing results in a form suitable for human comprehension. Babbage, for instance, had a plotter design for this purpose, where the actual output would be a graphical plot of the calculation. The era of the modern computer is ushered in by the mathematics of the 1930s. And the simplest kind of virtual computer is the finite state machine, which is the subject of this lecture. Now, the formalism for the finite state machine is defined as a tuple with 5 elements. The elements are either sets or functions, and we have 3 sets and 2 functions. Our 3 sets are the set of inputs. For instance, if the finite state machine were driven by a 0 and a 1, binary valued, then the set of inputs would be equal to 0, 1. O, which is the set of outputs, Q, which is the set of states. The set of outputs reflects the observables from the machine. That's what you view or observe while the machine is running. Q are the set of internal states that you don't see. So what you see or hear are essentially found in O, while Q reflects the states that the machine goes through. Now, the machine goes through these states using this very important function, delta. So delta is called the transition function, and it's defined by as follows. You have a current state from Q, an input, and that takes you to the next state. Now that next state may be very well the same state that you started with, or it could be another state within the set Q. So the presence of Q on the left-hand side and Q on the right-hand side doesn't mean that these are the same states. It just means that any particular state may be picked from the set Q. Finally, lambda represents the output function. And one of our definitions for lambda is where we take the state set and map that to O, which is the set of outputs. Our first example is going to be coin flipping. For the coin flip exercise, we're going to draw 2 states. So let's draw the first state right here, and we'll draw the second state right here. Now this first state over here is going to represent when the coin is heads, face up. So we'll just represent the heads by just saying H. And then when the coin is tails, face up, we'll just put a T right here for tails. So then each of these circles then represents a corresponding state for the coin. When we flip the coin in the air and it lands on our back of our hand, our palm, or on the table, and it is face up with heads facing up, then it's in this state. When the reverse is true and the tails is facing up, it's in this state. In order to get from one state to another, basically we need to provide input to this system. And input to this system is achieved by flipping the coin. So the flipping of the coin is really the input. We can say that when we're flipping the coin, we're providing an input of 1. So we'll just put a 1 there. And we're not flipping the coin at all. When we're not doing any flipping, we'll just say that we have a 0 input. So we'll put a 0 over here, and we'll put a 1 over there, like that. The second example is an example of lights that you might find in a hotel room, along with a knob that you turn in order to change the lights from one position to the next. This is the scenario for the bedroom that you have in a hotel. Let's say we've got 2 queen-size beds. This is bed 1 that we're looking at, and this is bed 2. Now over here we have 2 lamps. So this is lamp 1, and this is lamp 2, and this is a lampshade for lamp 1, and the light comes down here onto that bed. This is a lampshade for lamp 2. The light comes down here. Now over here we don't have a button, we have a knob that can turn. And by turning the knob, we change the state of both of these lamps to on or off. And we do so as follows. First of all, let's say they start in the off state. That is to say that L1 is off and L2 is off. As we begin turning this, L1 will come on, then L2 will come on, and then both will be on, and then the next state after that is that they're both off, which is how we started it. So what we can do is we can draw a finite state machine then for this as follows. We'll go ahead and just draw it up here. We'll say that we have a state off, and that's when both lamps are off, and then we have a state when L1 is on. We have a state when L2 is on, and then we have a state right here where L1 and L2 are on. So this is a four-state finite state machine, and this is very typical of the kind of switching that you'll have in a hotel room for lights, or perhaps in your house if you've got a multi-way light bulb, multi-switch capability. So let's go and put the transitions on this finite state machine. We'd say that it goes from off to L1 when we turn the knob. So turning the knob will be the equivalent of giving the system an input of 1. If we don't touch the knob at all, it will be equivalent of giving the system an input of 0, which is default. So we can go ahead and make reflexive arcs with 0 on each state. That just means that nothing is pressed once you're in that state. But to actually move from one state to the next, we actually have to turn the knob. So moving from off to L1 to L2 to L1 and L2, all we do is turn the knob or provide the machine with an input of 1. Going from L1, L2, where both lamps are on, all the way back to the beginning, means that we just do this. We have a final transition that we label with 1, and that takes us back to the start. Your average digital watch has controls that are really based on finite state machine execution. The main input for your watch is something we'll call the mode select, and if you have a digital watch you may very well have a button that's labeled mode. The mode switches the watch to its key supported modes such as time, alarm, timer, and chronograph. Time tells the current time, alarm is where you can view and set the alarm. Timer will count backwards from a specific time, and then chronograph will count forward as if you were to time laps and runners. These represent the four main states of the watch. Moving from one state to the next is performed through the button input. If you like, you can consider the pressing of the button to be equivalent to an input of 1 to the machine. Not pressing the button provides a default input of 0. From each state, there are certain other buttons that you can press, with each button having a different effect depending on the current state or mode. You may have played an adventure game on the computer at some point. You're in a dark dungeon, for example, and you have various commands that you can issue to the computer. Each command takes you to a different outcome. The commands may be specified by voice, by mouse clicking, or by entering text, as in English, or some other natural language as to exactly where you'd like to go, with some outcomes involving movement to yet another location. So each location in the adventure game is a state, and then each command is really an input. The machine captures the logic of the adventure game, and the output of the machine can be purely textual, as it was back in the late 70s and early 80s in adventure games, or it can be in terms of 2D or 3D graphics.